Okay, hi everyone, it's Mr. Mellinger, and today is Sunday, March the 10th. So I'm going over the assignment that you should have done in class tomorrow. I want to make a correction as to what I said on Friday. What I would like you to do is be sure that you have the day, the March 7th assignment says due Friday, March 8th. Be sure you have that done first thing on Monday, and that's what I'm going to talk about today. I asked you to read the notes for about the first 4 pages. So these are the VSEPR, we'll define what that means, and molecular orbital sheet. And I would like you to read that, including the diagrams that you see on these 2 pages, 3 and 4, or 2 and 3 rather. And I'd like you to read that until you get to the bottom of page 5. So read it down here where you have this image down here, okay? Just read that. You don't have to do the assignment. We're going to do that in class. All right, but I would like you to read this and be familiar with this sheet and the terminology of the first 5 pages. So what we're going to do is do what we're doing in class, and we're going to finish this up drawing Lewis dot structures for molecules. So I just want to be sure everyone has a clear explanation of that and does the rest of that assignment. What you want to do is look at your notes on chemical bonding, and down at the bottom of about the 7th page, you'll see drawing Lewis dot structures for molecules. So you want to find those instructions and just follow that as a kind of checklist. Check off each step as you go down, and this will kind of be your roadmap of how you draw the Lewis dot structures for molecules. It's not always, the rules aren't always followed. There are some exceptions, but generally speaking, you can follow these rules and complete these molecules. I'm going to keep this off to the side, but you can have that out and keep a reference. And as I say, use it as a checklist, okay? So let's get started on these molecules right here. Okay, so the first one is phosphorus tribromide. We're going to draw the Lewis dot structure for that. And so if you look at your rules and follow along with me, determine the total number of valence electrons. So I'm going to come over here, and you'll notice this is a sheet that I've modified to be able to fit all of this on the sheet. Your sheet does not give you this much space, so please do this on lined paper. Okay, so you have phosphorus, and okay, so for phosphorus tribromide, we have 1 atom of phosphorus, and we are going to, excuse me, damn it. Okay, excuse me, I had a brief interruption there. So we've got 1 atom of phosphorus, and we want to count how many valence electrons it has. So remember, we do that by counting across the row. So phosphorus is right here, so it is 1, 2, 3, 4, 5 elements from the left. It means it has 5 valence electrons. I'll go ahead and write that right here. And then bromine, we have 3 of those, and they each have 7 valence electrons. So we have 5, 21, we sum those up, we get 26. So we need to account for all 26 valence electrons, okay? All right, so you put the least electronegative element in the middle. Also, kind of a rule of thumb is usually if there's only 1 element and 3 of these, the P is going to be the one in the middle. And because we don't know any better, we're just going to draw it somewhat symmetrically. We could draw it kind of like a triangle, but we'll go ahead and just put them on these 3 sides like that, okay? All right, so that is the first step. The least electronegative atom, by the way, is, the least electronegative element is phosphorus, so it does go in the middle. Where you can find that information is on the colored periodic table that I've given you. And here it is. We don't use this a lot, but now we're getting into some concepts that the extra information that this table gives you will be useful. You go over to the back side of it. Got to flip it over like that. And in the upper right-hand corner for phosphorus, we see 2.19. I know you can't see it on the screen here, but you can see it if you have the table in front of you. And for bromine over here, we have 2.96. So phosphorus is less electronegative than bromine. Okay, so we've taken care of that. We've positioned phosphorus in the middle. And any hydrogens and fluorines go on the outside. Those are terminal positions. We don't have any of those. 2C, connect the outside atoms with the central atom using single bonds. Okay, so we're going to do that. And there's a bond there, single bond. So again, each of these elements contributes one electron to its shared electron pair. Bromine contributes one of these, phosphorus contributes one of these in each of these cases. Okay, the next thing it says to do is place the remaining electrons to create octets. Well, we see we've used up 6 electrons so far, so we're just going to do that. We're not going to even count at this point. We're just going to put them around there to create octets. Okay, and there we've done that, and 2 more down here on the bottom of phosphorus, okay? So there we go, we've done that. Okay, now let's count. Bromine has 8 here, bromine has 8 here, bromine has 8 here, that's 24. And then phosphorus, we've already counted these 6 right here for the bromines. Phosphorus has 2 more at the bottom, so that's 24 plus 2 is 26. And that's exactly how many we need to use. So remember what you're shooting for. The 2 things you're shooting for are this. First, use all of the valence electrons. And second, create octets. So we've done both of those things here. Everybody has an octet. We've used all 26. We're done. That's the Lewis dot structure for phosphorus tribromide. Okay, let's keep going on now. We have N2H2. We're going to just put the N's in the middle. Not because they're the least electronegative, but because the hydrogens must go on the outside. And we'll just create a symmetrical structure because we're not sure what the geometry of this structure is at this time, but that's a pretty logical guess. Okay, so the next rule we're going to follow is, well, we count all the valence electrons. That should be the first thing we do, so let's do that. We have 2 nitrogens, and each nitrogen has 5 valence electrons, so that's a total of 10. And then hydrogen, we have 2 hydrogens, and each one has 1 valence electron, so that's a total of 2. So you have a total of 12 valence electrons, okay? So there's 2, and there's 2. So we've used up 6 out of the 12 right there. So we still need to have some more. So the next rule, number 3, is it says place the remaining electrons to create octets. Well, hydrogen already has a full octet. It can only handle 2 electrons, so you can't place any around hydrogen. Okay, so we'll place them all around the nitrogens here. So that both nitrogens have 8, and the hydrogens each have 2. Okay, so let's count how many we have. We have 8 right here, and then we have 9, 10, 11, 12, 13, 14. So we have 14 electrons. That is 2 more than that's 2 more than we're allowed to have. Okay, so what we need to do is so that we have an octet. Again, this is where there's no hard and fast rule. You kind of just have to be creative. It's a little bit like a puzzle. But what we can do is we can place 2 of them here. Now we haven't changed the number of electrons, but we can place 2 of them in the middle here. And you'll learn to do this instinctively with a little bit of practice. Okay, so now everybody has an octet except this one has 2 extra. So if we get rid of these 2, so the first 2 we placed at a different location, these 2 we're just totally eliminating. Okay, so let's see if we have octets. You have 1, 2, 3, 4, 5, 6, 7, 8. Remember, the nitrogens share these 4. They count for both this nitrogen and for this nitrogen. Okay. However, in this number, let's be clear on this. In this number, you don't double count them. Okay, all you simply count is how many dots do you have. You need to end up with 12 dots. But for the purposes of covalent bonding, when atoms are forming their octet, you double count electrons that they share. So for octet rule, you double count, but for this, the total number of electrons, valence electrons you're using, you do not double count these two here, okay? These two pairs here, okay? So 1, 2, 3, 4, 5, 6, 7, 8 for this guy. 1, 2, 3, 4, 5, 6, 7, 8 for this guy. We've used a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've done both things. Everybody has a full octet. We've used all 12 electrons. So that's the structure for N2H2. Okay, let's keep going. Now we have one CH3OH, right? So what you're going to do with this is, you know, the hydrogens have to be on the outside, and the formula gives you a clue as to the structure. Why did they put 3 H's here and then stick this H outside of the O here? Why did they do that? There must be a reason. Well, it does give you a clue to the structure. So we're going to first count our electrons. So we have C, we have 1 carbon, and carbon has a total of 4 valence electrons. Hydrogens, we have 4 hydrogens, and each one has 1 valence electron. That totals 4. And then we have oxygen. We have 1 oxygen, and that has a total of 6 valence electrons. That's 6. So we have a total of 6, 4, 4, 14 electrons in all. Okay. All right. So let's go ahead and draw the structure similar to the way the formula is written. We're going to put a C here. Let's put an H on 3 sides here. Then we're going to put an O here, and then we'll put that other H out here on the outside. And as it turns out, this is actually the structure of the molecule. Okay. All right. So next rule is we're going to create single bonds. What you want to do at that step is you want to see, have you used up all your electrons at that point? So we've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've used 10 out of the 14. So we have not used all of the electrons. So what we do is we finish by creating octets around everyone else. Well, the only one that doesn't have an octet yet is oxygen. Hydrogens can only take 2 electrons. That's their octet. Carbon already has 8. So we're going to put 2 lone pairs here and here. And that does give us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So everyone has an octet, and we've used all 14 electrons. So this is the final structure for our molecule. Okay. Next, let's go on to NO2. And logic would tell you that if you have 2 oxygens and 1 nitrogen, well, nitrogen is less electronegative than oxygen. So we're going to just make a symmetrical molecule like that. Just assume it looks like that. That's called a linear molecule. We'll talk about geometries later this week. All right, and what this means is you're going to have an extra electron here, okay? So let's go ahead and count this up. So nitrogen has 5 valence electrons. There's 1 nitrogen. 1 times 5 equals 5. And oxygen, there's 2 oxygens. Each one has 6. So that's 12. That gives you 17. And then it tells us we're going to have an extra electron. This is an ion. Okay, it's a nitrate ion. So what we're going to do is add 1 more electron to that. And that means we have to end up with a total of 18 electrons. Okay, so let's just go ahead and follow the rules. Create single bonds there. Clearly that doesn't use up all 18. So that means we're going to next go ahead and put octets around everybody. And now we count. We have 8 there. We have 8 over here. That's 16, 17, 18, 19, 20. So we have 2 more than we need. So what do we do with that? Well, again, we have 2 more than we need. We're going to have to get rid of something. It's most likely going to be on nitrogen, right? Because if you change one of the oxygens, it's possible they won't have an octet. So how can we arrange the nitrogen atoms so that they produce an octet? I'm going to erase that, and I'm going to put it in there. Okay, so I made a double bond there. But now this nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. And a double bond there and a single bond on that side. Okay, so we have used a total of 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 okay? So what we need to do is we have two, this oxygen has more than an octet, it has 10 electrons, so we need to get rid of 2 of them. Generally you pick the ones at the end so that it's symmetrical. So now oxygen has an octet, 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen has an octet, 1, 2, 3, 4, 5, 6, 7, 8. And this oxygen clearly has an octet. And we've used up 8 plus 6 is 14, 15, 16, 17, 18. So we've used all our electrons and we filled an octet. Now notice the double bond, you could have flipped this and just turned this around and made a mirror image. The double bond could have gone on this side, and this lone pair over here could have gone on that side. So you have 2 different possible structures for that molecule. That's called a resonance structure. It just simply means 2 possible structures for the same molecule that would both obey the Lewis dot structure rules. Okay, we'll talk a little bit more about that. We've talked about that already, but we'll, anyway, that's the resonance structure. Okay, let's keep going. Okay, C2H4, so you're going to have 2 carbons. Hydrogens have to go on the outside. You can either draw them off at an angle like that or just draw them above and below. But they should be symmetrical. It looks like it's going to be a symmetrical molecule. Okay. All right, let me just draw a little line here. So we're looking at carbon. We have 2 of those. Each one has 4. That's a total of 8. Hydrogen. We have 4 of those. Each one has 1 valence electron, so that's a total of 4. You add that up, you got 12. You don't have any charge on this one like you did on the one up above, so it's just 12. So now we go ahead and we connect everybody with single bonds. And we have all the hydrogens have their octet, they're 2 electrons. The carbons don't have their octet yet. So the way we could do that is by putting a double bond in here. And again, these double bonds count for both this and both this. They don't count in terms of double for this number, but they do for the octet rule. So keep those 2 things straight. So 1, 2, 3, 4, 5, 6, 7, 8 for that carbon, 1, 2, 3, 4, 5, 6, 7, 8 for the carbon on the left. We've used a total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So everything works well, and that's our structure for ethylene right there. Okay. All right, keep rolling. Just draw some lines, be sure we're not getting confused here. So we have B, S, and F here. Okay. So boron. Excuse me. So boron, there's 1 boron. The boron has 3 valence electrons, that equals 3. Sulfur, there's 1 sulfur, and that has 6 valence electrons. And 1 fluorine, 7 valence electrons. Okay, you got 13, 16 total electrons here. Okay, now which one goes in the middle? You got three different elements here. So let's look at the electronegativities and let's see if it follows the rules, because I'm going to give you the answer, but let's see if it follows the rules. Hopefully it does. So if I go over to the back side of this colored periodic table, realize you can't read it, so I'm going to read it for you here. It's 2.04 for boron. It's 2.58 for sulfur. And for fluorine, the highest electronegativity of all, it's almost 4. That's almost as high as you get at 3.98. So the lowest electronegativity was the 2.04 of boron. So that one should go in the middle. And in fact, it does. And again, for lack of knowing anything other than how to draw this, we're just going to assume it's a symmetrical structure. So we're going to put the F here and the S here. You could have flipped them around, but we're just going to go ahead and do it like that. Okay. So we've counted our electrons. We got 16. We're going to create single bonds. Of course, that doesn't use up all the 16, so we create octets around everybody. Okay, so now we have 8 on this side. The way I usually count them is 8 on this side, 8 on this side, and 1, 2, 3, 4 more. So that's 20 in all. So we have too many here. We only need 16. We have 20, okay? Usually when that happens, you're going to create you're going to create a double bond somewhere, all right? So let me go ahead and going to take, well, how could we do this? We do this a number of ways. We could take 2 off of here and put them right there. Okay, so now we have 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so we still have too many. So let's get rid of, again, you kind of play around with it a little, but if we get rid of these 2 on boron, then we have 8 and 8, and you have 3 here. Okay, so what does that give us? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. But boron doesn't have an octet. It only has 6. Okay, so we're back and we have a structure for our compound, which is BSF. Okay, but there's first 2 things. One is boron is one of 2 elements that occasionally, in fact, often violates the octet rule. You'll notice that boron only has 6 electrons. So you would not have been able to really do this unless you knew that exception. The other exception are aluminum. So exceptions, besides the obvious one of hydrogen and helium, which only can handle 2 electrons in their orbital, the exceptions to the octet rule are boron and aluminum. The reasons for this go way beyond the scope of this course, so we won't talk about that. Just learn them and learn that they often will only have 6 valence electrons rather than the 8 that you would expect them to have. Now let's do a little exercise here on something that we did in class. There's another possible structure that you could have had. This is a structure we came up with, but you could have also put the double bond over by fluorine and just switched a few things around, and you would have had, let me erase this. Okay, so let me rewrite. I just did a little calculation here. Let me write it larger. You don't have to do this, just watch it. It doesn't hurt. Every time you do something, you become better at it. So this is what our structure looked like. It has boron here with 6 valence electrons, and it has fluorine over here with 8, and the sulfur has 8 with a double bond. So let's do a formal charge on this. The other possible structure, let me draw that first, could have been S with a single bond and 8 valence electrons shown here. Boron is here, and the double bond goes over beside fluorine. So in both cases, we used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons in both of these cases here. All right, so let's do formal charge to decide which one of those is preferred by nature. There's 2 things to understand about formal charge. One is you want the formal charge closest to 0 on all the atoms. Make sure I don't go off screen here. Okay, let me restate this. Okay, number 2, let's try again, take 2. Okay, you choose the molecule with the most negative number on the atom with the highest electronegativity. Let me give you an example. Let's say you had 2 molecules. Okay, they both have the same, the formal charge looks exactly the same on both, okay? but on one of them, the oxygen is the highest electronegativity atom. And let's say its formal charge is -2. And on another one, the oxygen, the formal charge is 0. This would be the one that would be the preferred molecule, is the one where the most electronegative, assuming oxygen is the most electronegative, would have the most negative number associated with it, okay? We'll get to examples of that and it'll make more sense. But let's go ahead and work this one. So let's do the formal charges for this. So for sulfur, let's practice this. Sulfur has 6 valence electrons. You subtract from that the number of lone pair electrons. Here it's 1, 2, 3, 4. And then half of the bonding electrons. 1, 2, 3, 4 divided by 2 is 2. And that gives you 0. Okay, good for that. Boron. Okay. Boron has a total of 3 valence electrons. It has no lone pair electrons, and it has 1, 2, 3, 4, 5, 6 bonding electrons. You cut that in half and you get 3, and that equals 0. Again, this is just the formula that you were given in class for formal charge. Fluorine, you count the number of valence electrons it has. There's 7. You subtract from that the number of lone pair electrons, 1, 2, 3, 4, 5, 6. And half of the bonding electrons, there's 1, 2, half that is 1, and that gives you 0. So this is perfect. 0, 0, 0 is exactly what you want to see. But let's do the other alternate structure and why we did not choose this one. Sulfur. Okay, it has, again, 6 valence electrons. Again, you don't need to understand why this formula works. Just understand how to use it. That's all you need to know. Okay, don't worry about the why. Like the quadratic formula in math. Don't worry about why it works. It just does. Okay, and then you have lone pairs, 1, 2, 3, 4, 5, 6. And then you have half of the bonding electrons for sulfur. There's 2 of them, so that would be 1. Okay, and that equals -1. For boron, you have 3 valence electrons, 0 are lone pair, 1, 2, 3, 4, 5, 6 divided by 2 is 3. It are bonding electrons, that gives you a 0. And finally, fluorine, you have 7 valence electrons, 1, 2, 3, 4 are lone pair electrons, and 1, 2, 3, 4 divided by 2 is 2 bonding. Okay, and that gives you +1. Now notice if you add up the charges for this second structure, you get a 0. In both cases, you get a 0. But this one, all of your numbers are 0. In this one, you got a -1 and a +1. So nature does not prefer this one. Nature prefers this one because everything is closest to 0. We didn't have to apply this other law over here about the most electronegative, so we'll talk about that at some other time. Okay, let's keep rolling here. And okay, so we have HBr. Okay, so there's only one configuration that can have something like that. Okay, we're going to say H has 1 times 1 electron, and Br has 1 times 7 electrons. It's a total of 8. So we got 2 there. So let's do this. 3, 4, 5, 6. So we have excuse me, I'm sorry, 1 times 7 is 7, but when you add them together, you get your 8, and that's why HBr is pretty easy to draw. There's the 8 electrons, everybody has an octet, everybody's good. Okay, finally, let's do this one again. Take a cue from the chemical formula as to what the structure is going to be, okay? So we got a couple of carbons that are co-equal. We got 5 hydrogens, so we're going to put one here. Put one here, put one terminal out here at the end, another one. They're all really terminal because they're on the outside. So there's your C2H5. Then we're going to come over here and draw an O and then another H. And you can see that pretty much figure that's got to be the structure of it based on that chemical formula. Okay, so what do we have? We have hydrogen. We have 5 times 1 equals 5 total valence electrons. Carbon. We have 2 times 4 equals 8 valence electrons from carbon. And oxygen, we have 1 times 6. Okay, and you get 15, 19. Now 19 is going to present maybe an oddball situation. Maybe, maybe not. So let's go ahead and see how it works out. So we're going to place bonds between each one. Sometimes odd number of electrons can be problematic. It might indicate an ion, but not always. Okay, so we've got a single bond between everybody, so let's count how many of the 19 we've used. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16. So we need to use 3 more, okay? Oxygen still doesn't have an octet. And I can see H5C2, 5 and O, it's got 6. Whoops, I blew it. I have 6 hydrogens, don't I? So I really don't have an odd number. Forgot to count this guy out here. So you have 5 plus 1 is 6. That makes it 6. That makes it a nice even 20. This would have had to have been an ion if I had done it the way I did it. So again, 6 times 1 is 6. Now you add up, you got 20. So let's see if we've used up 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Everything's good. Just nice series of single bonds there. And that's all there is to that. Okay, let's go a couple more. The last one's going to be a little bit unusual one, and we talked about it in class, but I'll explain it to you again. So we have N2F4. So again, just assume that it's going to be symmetrical. Fluorine is the most electronegative. So that means nitrogen being a less electronegative is going to be the central atoms. So we're just going to draw it like that. And we have N, we have 2 of those. Each one has 5 valence electrons. That gets you up to 10. And fluorine, we have 4 of those times 7 valence electrons is 28. So we can have a lot of electrons here, 38 electrons. So let's go ahead and just start drawing the octets, because we know that these 4 right here are not going to do us a lot of good as far as filling everything up. So let's go ahead and put octets around everybody. There's not a bond between these two, okay? There is a bond between these two. They're the central atoms. These guys are outside. But you can put lone pairs around here. Okay, and also around these 2 guys out here. Okay, wow, that's a lot of dots to count here. So let's just look at it this way. There's 8 for that fluorine, 8 for that fluorine, 8 for that fluorine, 8 for that fluorine. That gets you up to 32. And then you have 33, 34, 35, 36, 37, 38. Boom, that's it. That's all we need to do on that one. And okay, and finally SF6. Okay, so this is a funny one. There's only one way you could possibly draw this, and that's to put these fluorines around the outside like this. Okay, and I got 2 dots there, and I got 2 dots there, 2 dots there, 2 dots there, dots and dots. Okay, so I have 1, 2, 3, 4, 5, 6 sets of 2 dots. That's a total of 12 electrons. By the way, I didn't count my electrons at first, so let's go ahead and do that. So you're going to have fluorine. Let's do it down here. Fluorine is going to be 6 times 7 equals 42. And sulfur is going to be 1 times 6 equals 6, so that's going to be 48. So we're supposed to have 48 electrons. No, I'm not supposed to do this, but I'm going to go ahead and just use lines real quick to represent the lone pairs of electrons. You're not supposed to use lines for lone pairs, but I'm just trying to save a little time here, drawing a million dots here. Okay, so we got that, that, and that. You got that, that, and that. Okay, so we got 1, 2, 3. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 times 2. Each one of those represents 2. That's 36. okay? And then we've got 36, and then we've got another 12 that are inside of here, right there, that I've already drawn. That gets us up to 48, okay? And that's how many we've used. Now the question is, how can this sulfur have it has 12 electrons surrounding it? That violates the octet rule. And we talked about this concept that if you get any element that's in the third row or below down, it actually, the central atom can actually hold more than 8 electrons, more than an octet. Why? Well, because the octet would be, in the third row would be 1, 2, 3, 4, 5, 6, 7, 8. Each one of those contributes an electron. That would be 8 that the third row could handle. But then the third row also, remember, it extends down here. The third period. There's 10 different spaces down there. And you can almost think of that as overflow storage for anything that's in the third row and below. So you can have up to 4 more electrons fitting down into the d orbital down here, okay? And that's the way to view that. So you can fit 8 in the standard s and p orbitals plus 4 more in the d. Now you may say, well, look at all this space in the d. Why can't you fit more than that? Why can't you fit 14 or 16 or 18? And the answer is just simply you can't, okay? Beyond that, I couldn't explain it. I won't try to explain it to you. It's not significant. Just understand that you can have what's called an extended octet of 4 electrons beyond the 8 standard octet electrons. Okay, so that would be 12. And in this case, you would have those. There they are right there. There's 12 electrons surrounding the sulfur, and that's perfectly legal. You can only do that for third row and below. Just keep that in mind. Okay. All right, so the next two, explain how an ionic bond and a covalent bond works. I want you to write that out. Every so often, we got to be sure that you're really clear on what an ionic and covalent bond are. So I'm going to ask you to write that out again. That's really a review question. I won't do that here. It is on the slides, and you just have to go and locate those slides, okay? It would benefit you to go back and reread the slides every once in a while. We're going to use PowerPoint slides less and less as we get into more complex topics, but they are on the PowerPoint slides from earlier in the course. Okay, and we've got one more set of problems to do. And I will try to find those. There they are. And I ask you to do z effectives on several elements. Okay, and then I do want you to know how to write this explanation for the test on Friday, which would be Friday, March the 16th. Be sure you can write this explanation for 14. Let's just go ahead and do this. So what's the z effective for lithium? Just remember, z effective is, let's write it up here. It's the protons in that atom minus the non-valence called core electrons. They're not called non-valence, but I want to be clear what they are. The non-valence, they're called core electrons. Anything that's not a valence electron. What it's basically saying is how much that the outer electrons are being blocked out by the inner electrons from the nucleus, and therefore, if there's a lot of blockage, if they're really obscured, those outer electrons from feeling the pull of the protons, then they are going to be more easily ionized, and it means that the radius of the atom will be larger because they won't be pulled in quite as much. So here we have Z effective, and if you grab your periodic table, okay, so lithium has 3 protons. Now, to do a little mini diagram of lithium, it's got the 3 protons in the middle, it's got 2 core electrons, and then in the second orbital, it's got 1 valence electron. So these 2 core electrons are one we're interested in for this. So minus 2 equals 1. So it means that outer electron is effectively not feeling the pull of 3 protons, which lithium has, but effectively only feeling the pull of 1 electron because these 2 are blocking it from feeling that pull of the protons, okay? Excuse me, it's feeling the pull of 1 proton. These 2 are preventing it from feeling the pull of all 3 of the protons, okay? Carbon, let's do the same thing. Let's do a little sketch. So carbon has 2 core electrons, and then it has 1, 2, 3, 4 valence electrons. Now, these valence electrons do not block each other out. They're side by side. Just think of them as that. They're side by side. They're not blocking each other from feeling the pull of the nucleus, the protons of the nucleus. So carbon has a Z effective of 6 protons in the nucleus minus 2 core electrons, which equals 4. Okay, so each of these electrons will effectively feel the pull of 4 protons, not 6. All right, neon, let's do the same thing. So neon, we have 2 core electrons, trying to draw big dots there. And in the second orbital, we have 1, 2, 3, 4, 5, 6, then kind of missed on those two, 7, 8. Okay, again, these 8 on the second orbital are not interfering with each other or keeping each other from feeling the pull of the nucleus. So the Z effective is the number of protons that neon has, which is 10, minus the core electrons, which is 2. So those outer electrons in neon are still feeling a pretty strong pull from the nucleus. They're feeling as though they're being pulled by 8 protons. That's pretty good. Compare that to lithium, which only feels 1 proton pull. Its outer electron only feels 1 proton pulling on it. Okay? All right. Sodium. Okay, so I'm just going to knock down the numbers here. Sodium has got an atomic number of, or number of protons of 11, and all but one of those is a core electron. It's either in the first or second orbital, and sodium's valence electron, the only one it has, is in the third orbital, so you're going to subtract 10 core electrons, and that's going to give you an effective pull of only 1. So it still feels only 1, just like lithium. Very, very weak pull. So that outer electron is easily ionized. It's easily pulled away from the sodium atom. Okay, silicon. Silicon has got 10. It's got an atomic number of 14. So its Z number is 14, but its effective Z number is going to be 14 minus. And if it's in the third row, it's going to have 10 core electrons from all the electrons from the first 2 rows, okay? So it's going to feel an effective pull of 4, the same as carbon, okay? That's why elements in the same group or column tend to have similar properties, okay? They have, the elements carbon and silicon have a lot in common because they're in the same group. Finally, chlorine. Chlorine, the Z effective for that is 17. And you're going to subtract from that, again, it's in the third orbital, so that means all the electrons in the first and second orbitals, there's 10, are going to block it out, so it has a Z effective of 7. So that's pretty strong. That's held a lot stronger than any of the other elements in the second or in the third row. Okay, that's that. Okay, let's do this. Here's kind of an essay question. Use Z effective for chlorine and sodium. Explain why chlorine has a smaller atomic radius than sodium, even though chlorine has more protons, okay? So the explanation for that is simply going to be chlorine, let's just figure the Z effective number. Chlorine has a Z effective of what we just figured out. And sodium has a Z effective. And if I were to ask you this as an essay question, show the calculation, okay? That's just a simple subtraction, but we've already done it here. So sodium has a Z effective of 1, okay? So the atoms, the electrons for sodium and chlorine let me just not say sodium and chlorine. For sodium, the electrons for sodium in the valence shell or orbital feel the pull of only 1 proton. the electrons for chlorine and I should put little pluses and minuses here, feel the pull of seven protons. Therefore, the valence electrons for chlorine are pulled closer to the nucleus. Creating a smaller, let me write that better, atomic radius. Boom. Okay, that's it. All right, so that's it. Okay, so I'm going to stop this. I want you to read the first 5 pages. Try to make as much sense out of it as you can. We'll talk about it in class tomorrow. And but come in with this assignment completed. Okay, we'll hand it in right at the beginning of class. Have a good day.